Hi, and welcome to General Chemistry. I'm your professor, Dr. Robin Bond. Now, I like to start my chemistry classes by talking about why we want to learn what we're learning, in this case, the basics of chemistry, general chemistry. This is particularly important for those of you who are taking this course because you, quote-unquote, have to. At my last school, I used to teach a lot of pre-med and pre-pharmacy students, all of whom only took chemistry because they had to. And even at Evergreen, where you technically aren't required to take any particular class, many students are told that if they really want to understand biology or marine science or ecology, they have to take chemistry. And that's why a lot of people take this class. So I could start off by giving you some really logical statements about why we study chemistry, like the world runs on chemical reactions, which is 100% true. There are very few reactions that aren't chemical in nature. Some of them are physical, but there's a lot of chemistry going on all around you right now. Basic principles of chemistry help us explain other sciences, biology, geology, and medicine, even psychology to some extent, just a lot of things. When we're talking about lab, it is a lot easier to do chemical reactions and predict the outcome than it is to do things with, let's say, bacteria. And I'm saying this as someone who worked with bacteria for my graduate thesis work. Bacteria do whatever the heck they want, and sometimes it's what you expect, and other times it's not. So the things we're going to be talking about in the first half of general chemistry really stem from two basic ideas. One is the structure of the atom. That helps us explain virtually everything else that's going on. And then using measurements to evaluate systems. And those things help explain all sorts of things like chemical reactions, why different chemicals react with each other, how atoms connect to each other, why do we get energy out of chemical reactions, how do molecules connect to each other, what shapes do molecules take. All of these things are based on our knowledge of the structure of the atom and how we can evaluate those systems made up of atoms by using measurements. So let me explain why chemistry is important from a less logical perspective. Let's dive into an actual story. I've still never yet gotten pictures of my actual secret brownie recipe, but I do have a family recipe. I like to joke that I married my ex-husband to get the recipe. They're really good, and it's very sad I can't even eat them anymore. But every time my kids make them, I smell, and I'm like, ooh, I remember these. They make my mouth water. So it's a really great recipe that we don't share with anyone who's not actual family. In fact, I was told we don't even share it with my sisters. So my sisters don't even have that, only my kids. So when my kids were growing up, every time there was a bake sale fundraiser or something like that, they would make our special family brownie recipe. And everyone would be like, oh, these are good. I want the recipe. And we'd say, sorry, if your kids want to, marry one of my boys or something, maybe you can get it. But that's pretty much the only way. And most people would laugh when I said something like that. And they'd say, well, I'll just wait till the next bake sale and I'll get more. But I had one friend who was determined to figure out my secret recipe. And so she went and she looked through all her cookbooks and she found one that she thought was reasonably close. And she said, I'll start with this. But Robin's brownies, they're a little gooier. And then she had to stop and think, what makes things gooey? Is it more chocolate? Is it more butter? Robin's brownies are richer because these things are really rich and gooey. So what might make it richer? Is that more butter? Is that more eggs? Right? What is it? And she went through and she kept trying things and she's like, I think this is close. What do you think? And she actually figured it out. But it took her like 4 years of trying before she actually figured out the recipe. So that was her personal triumph. She figured out my secret recipe. But now let's think about what it means to understand what things are made of. First of all, it wasn't just what went into the brownies. She figured that out really quickly. I think the cookbook recipe she got had exactly the same ingredients, just not in the same quantities, right? So we need to know how much and not just what. But if we know what something is made of, one of the things that we can do is, okay, yeah, sure, you can duplicate the previously existing material. So she could make the brownies I had made for her. But you can also change that previously existing material to have different properties. So, for example, I know people who say my brownies are too rich and gooey. I don't know if there's such a thing, but, they're allowed to have that opinion. Well, if you understand what it is that makes it rich and gooey, you can just cut back on that ingredient, right? Now, obviously, everyone is probably salivating for brownies right now. And if we were actually in person in class, you would be eating my brownies because I do make them for students. Let's think about things that are maybe a little more useful than brownies. It used to be that if you had a fever, the best way to bring it down that we knew of, in the West anyway, was willow bark tea. Okay, so there was something in the willow bark that would help bring down fever. And obviously we didn't know much about chemistry when we discovered willow bark tea. But at some point, people figured out exactly what it was in willow bark tea that brought fever down. And it was this chemical that we call salicylic acid. Well, at some point, someone asked, is there any way we could change salicylic acid to bring fever down more effectively? And that person figured it out and made acetyl salicylic acid, which is aspirin. So that was the first synthesized fever reducer. Now, another thing we can do is, if you understand how something happens, so how a chemical reaction happens, that allows you to accelerate, slow, or reverse the process. So, for example, if you have something that rusts, you don't want it to be rusty. You want to unrust it, right? If you understand how things rust, you can, I don't think unrust is a word, but you can basically remove the rust, right? There's all sorts of things you can do if you understand the chemical processes. So this is what we're trying to do. We're trying to understand previously existing materials, whether those are the active ingredients of an herbal concoction like willow bark tea, whether those are things like a spike protein in a virus. We want to understand what that's made of, because then we can understand how those interact with everything else, and we can control those processes and the properties of materials that we make. Okay, so let's think about how chemistry developed, the history of how we got chemistry, using the cooking analogy. So the first thing that people figured out was, what ingredients are we working with? The things that we call elements. So, for example, people wanted to make weapons to hunt animals. And so they quickly figured out that some things were better for that than others, right? We started with, stone. And, around here you can possibly pick up some obsidian, which makes really great arrow points. But then people started getting into metalworking, right? And some metals seem to work better for some things than others. Gold is very easy to work with, but it's also soft enough that it doesn't make a very good tool, right? You whack something with a gold hammer, the hammer is going to bend and not whatever you were hitting with it. People started working with metals before 400 BCE, but that's where they were actually starting to think about, okay, what is the smallest particle that we can have of something without losing its properties? And that's definitely something we're going to talk about in a little bit. The second thing we need to think about is how much of each ingredient do we need for a particular recipe? Because remember, that sort of stuff ends up being important. Now, it's long before 1750, which is the date I have here. There were jewelers who had recipes, if you will, for alloys of metals, but getting very, very, very precise about amounts and understanding the reasoning behind why things combined best in certain ratios, that started in 1750, and we'll talk about the person who really got that going. Now, the third thing that people got into was how do we change the recipes to make, well, the chemicals or the, whatever, it's an analogy, so the food we really want. And this came very quickly. Once we understood what a recipe, chemical recipe, was made of, it was very easy to start tweaking those recipes. But until we got past that hurdle of quantifying things, we couldn't really start tweaking what existed naturally. So I'm going to use a few terms. We're going to start with a pure substance, which is something that you can pick up in many different parts of the world, and it's going to have the same chemical composition no matter where you pick it up. So let me give you an example of something that's not a pure substance. Granite. You can go out and you can look at granites out here in the Cascades, and they're going to look very different from granite that you find in Colorado. A lot of the granite in Colorado is kind of pinkish. It's still granite. It's very beautiful, but it doesn't look like the granite out here. Okay, so that's not a pure substance. Compare that to gold, which is gold, right? Gold is the same no matter where you get it. Water. Now, some water has salt in it, but you can always distill out the salt. Water is the same, whether you get it here or whether you get it in Florida or Antarctica or heck, even out in outer space, water is water. A mixture is something that contains two or more pure substances. Each of those components of a mixture has its own properties. Sometimes when you put those together, they have a very unique joint property that you only get in the mixture. So for example, salt water is different than pure water. We know this. If you ever try and drink salt water versus drinking pure water, that definitely affects your body differently. So there are two types of pure substances. The first is an element. An element is a pure substance that can't be decomposed into simpler pure substances without losing its properties. And of course, one of the first elements that people found was gold, because gold does not easily combine with other elements. Oxygen is an element. So we're gonna talk more about these later. A compound is a pure substance that's composed of two or more elements. And an example of this is water, which is made up of the elements hydrogen and oxygen. Another example would be rust. You can take pure metallic iron, put it in with pure oxygen, and very quickly it will turn into iron oxide, which is generally not something we like to see on our steel structures. Again, when we're talking about pure substances, the smallest possible bits, we can have atoms, which are the smallest piece of an element that can't be cut without losing the properties of that element. We can have molecules, which are the smallest piece of a compound that can't be cut without losing properties of the compound. Now, the difference between an atom and a molecule is you can get down to a single molecule, and if you cut it again, it breaks into some sort of different arrangement of elements, perhaps different molecules. Once we start building molecules out of atoms, you will probably understand this a little better. Okay, so what we're going to start out talking about is measurements. How much ingredients do we need for a particular recipe? And so what we really need to do is we just need to go to the basics. We need to start thinking about how much can we measure of each thing. And it says starting about 1750. What was happening in 1750? Well, there's all these people trying to understand why things were made out of certain things. And this started many years before, actually, with the alchemists. So the goal of alchemy was to turn what they call base metals, so things that are very common, like lead, into gold or other precious metals. So basically, let's make some magic. Let's turn something that's not valuable into something that is valuable. And none of these alchemists were successful. What changed, and when people started really understanding what was going on after hundreds of years of alchemy, was when people started measuring things. So this picture shows Antoine Lavoisier, who is the person who always makes it into the chemistry textbooks, and his wife, Marie Lavoisier, who does not usually make it into the textbooks, but she is also just as important to chemistry. You've probably heard this before, especially in biology. They talk about spontaneous generation, where people thought if the right conditions existed, something would appear. So in biology, it was maggots spontaneously appearing, magically or naturally, whatever you want to call it, out of nothing. Right? If you have meat that's rotting, maggots will appear. The chemistry version of that is, let's say you take something that's iron, like a razor blade. If you leave it out, it rusts, but as it rusts, the interesting thing is it actually gains mass. So things aren't disappearing, things are appearing. So people would say, oh, it's magically appearing. Well, the Lavoisiers decided to put this to the test. Were things magically appearing? And the way they did that was, you could see these glass balls and cylinders. They set things up so that those could be evacuated. So they would completely empty them, and then they would put in exact weight amounts of certain elements and watch the reaction. And we'll talk more about this when we talk about conservation of mass. Now, science, by definition, is something that is reproducible. And this is why Marie Lavoisier is so important, because although the picture shows Antoine holding the quill, it was usually Marie who was the record keeper, who kept extraordinarily detailed notes. And after Antoine Lavoisier's untimely death, because he was a French aristocrat who got beheaded in the Revolution, it was Marie Lavoisier who made sure that his work got disseminated to the public. So science is reproducible. Science is predictable. And when we say it's predictable, up till this point, science had been qualitative predictable. So they would make observations. Oh, it's changing color. You put these two things together, it changes from yellow to red or something. But science is also quantitatively predictable. And that's the genius of Antoine Lavoisier, is that he figured out how to measure exactly what was going on. Based on very careful measurements, he could figure out the ratios in which things combined. And that was really the beginning of what we call modern chemistry. Understanding chemistry is going to help us understand the world. Now, I know that seems like a super broad, sweeping statement, but as we learn basic principles, I'm going to tell you about applications. And so that I hope at the end of this class, you will have a good idea of how exactly chemistry explains so much about what's going on in the world around us. I hope this was helpful, and I look forward to seeing you again soon.